All right, hopefully you guys can hear me okay. I'm trying to show what slide I'm on, but I'm not having very good luck. Oh well, I'm on 16.4, the electric field. So if you are following along in your PowerPoint, go to that slide. So if there's a point charge, so that would be like this right here, and it's in the vicinity of other charges, it is going to experience a certain force, okay? So if we know the electric field, or we could say that the electric field at any point is defined to be the electric force per unit charge. Okay, so you can find the electric field if you have the force and what the charge is. Okay, so it goes on and it shows you a few of those same equations. So you can get the electric field using the electric force divided by charge. And of course, then that is one way that we can end up finding the force if we have the electric field and the charge. Okay, so we can just rearrange the equation. All right, so example 16.5. This says that a small sphere of mass 5.1 grams is hanging vertically from an insulating thread that's 12 centimeters long. By charging some nearby flat metal plates, the sphere is subjected to a horizontal electric field. Okay, so kind of like before, now we've pushed it away from the center. And it gives us the electric field already, okay? And it tells us that it's displaced 6 centimeters from the horizontal. So we know that the string itself is 12 centimeters, so we've got that length, and we've got this length, so we can definitely figure out some stuff from that information. Okay, so the first thing that it says is it wants us to find the angle that the thread makes with the vertical. Okay, and I just want you to look at this picture for a minute. Actually, I think I have this picture again. Oh, this slide, sorry, it goes through some strategies that it suggests that you should kind of think about whenever you're going through and doing these this example. Okay, I'm gonna skip through that. You guys can read that if you would like to. But this is showing you a free body diagram, and we've got both the lengths and the horizontal, and then we've got the length of the string, okay, and it wants to know the angle. So you guys remember we were able to find angles whenever we did inverse tangent. We usually would do inverse tangent of y over x, but we don't do y over x this time. Why not? Well, whenever you do tangent of anything, tangent is opposite over adjacent. So what is the opposite here of this angle? Well, that's the x in this case, right? The adjacent is actually to the y. Okay? That's this right here. It's opposite to the x, and it's adjacent to this y value right here. Okay? So whenever we go to do the inverse tangent, we need to do the inverse tangent really of x over y. So we have inverse tangent of our x value, which is, skipped one, which is 6 centimeters divided by 12 centimeters, which gives you this angle of 26.6 degrees. Okay? All right, so now part B says, what is the tension in the thread? Okay, so this is sort of similar to what we were having to do in the last example, where we're having to break it up into the x, y components. All right, well, the tension here is like this, okay? And we have this electric force that is happening in this direction, and we have this force of gravity here that's happening like that. Okay, now, does it give us the electric force that it's going in the x direction? No. So, but does it also give you, does it give you the force of gravity? Yes. Well, you can figure out the force of gravity because it gives you the mass. Okay, and then you can multiply it by gravity. So if we're going to do that, we can say the sum of the force in the y is equal to, now look at this. Okay, we've got a force of tension that goes in the y direction, and then we have a force of tension that goes in the x direction. But we're doing the sum of forces in the y direction. So see this angle right here? Is it opposite or adjacent to the y-axis? Well, it's right next to it, so it's adjacent. So in this one, we would say tension cosine theta. Cosine means it's adjacent. Okay, minus mass times gravity. Okay, that's this guy right here. It's going down, so it's minus. All right, so then we can solve for the tension because we could move everything over besides the tension. We could have tension is equal to mass times gravity divided by the cosine of theta. And do we have theta? Yes, we just found theta. Okay, so we've got mass, which is 5.1 grams. So you want to make sure that you get that converted over to kilograms. Times 9.8 divided by the cosine of 26.6 degrees gives you 0.0577 newtons. Okay, so that's giving you the tension. Now the last question that it asks us to find is the charge. Okay, so part C is actually asking us to figure out the charge. So that means that we are going to have to, in fact, figure out that whole x direction situation. Sorry about my messages. Okay, so we've got the sum of forces in the x is equal to the q times the electric field. Now, did it give us the electric field? It did. It actually said that the electric field was equal to this 7.2 times 10 to the 5th newtons per coulomb. Okay? All right, so it did give us that information. If we rearrange this right here to solve for the charge, we could do the force divided by the electric field. Okay? Now, what is the force? Well, we have this force, right? We know that this tensional force right here not only had y values, but it also had x values. But instead of saying tension cosine theta, we could say tension sine theta. Okay? So we could say tension sine theta divided by our electric field. Okay, so we've got our tension that we just found, which was 5.77 times 10 to the negative second newtons times the sine of 26.6 degrees divided by divided by our electric field here, which is 7.2 times 10 to the 5th newtons per coulomb. It's going to end up giving you about 40.1 nanocoulombs. So whenever you plug that into your calculator, you should get like it might not give you 40 times 10 to the negative 9th. Sorry. I'm going to have to stop this